So a very good question will be, how are we supposed to do these by hand? And I thought, well, I didn't do them hand drawing, but I did go out and use Microsoft Paint to draw the level curves to this by hand. So first we sketch a contour of the map, and if we let z equal 0, then we have the point 0, 0, so that's here. If we let z equal 1, then we have the equation x squared plus y squared equals 4. Recall, this is our equation, so if you put 1 in here, multiply both sides by 4, you got 4 equals x squared plus y squared, so you got a circle with center at the origin and radius 2, and that would be this one, right? Same story with if z equals 2, then x squared plus y squared equals 8, and the circle, center at the origin, radius the square root of 8, that's 2 square roots of 2, that's about 2.8, and we got this circle. And I think you can see how that goes along. When finally when z equals 4, we have x squared plus y squared equals 16, so it's a circle with center at the origin and radius 4, and that's the one I have there on the outside. So here's another contour map. This is the contour map of the hyperbolic paraboloid, and one could call this a saddle. So if you can see that saddle there, that's what our picture is of. And so we want to look at the level curves underneath it in the XY plane, and I hope you can see that. If you can imagine passing a plane through this thing, well, maybe you don't even have to imagine it. I'll do one. So alright, I took the time and trouble to put in like g of xy equals 1, and if I do that, you can see quite clearly this hyperbola, which is reflected down here in the xy plane. And I could move it up a little bit. Suppose I said let g of xy equal 2, then you should see that same curve moving up. And then that one, and we could say g of xy equals 4, so it moves up further, and you might be able to figure that's what these traces are. Actually, I'm drawing them the wrong way. Take this straight down here, and we're looking at these traces in the xy plane. Those are the level curves. Let me see. I didn't try a negative value. Let's say -1. What do I get then? Well, then I get something that's going in the other direction. See this intersection of the surface and that plane is then drawn down here in the xy plane. And if I went -4, you can probably see the same phenomena, right? There it is, over here, back here. And those are the level curves. So we can't draw it anymore, but we can talk about level surfaces. Now, level curves are in the xy plane. Level surfaces are in three-dimensional space, so the concept of a level curve can be extended to functions of 3 variables. Just don't ask me to draw it anymore, but because then we'd have to have 4 dimensions, and that's not possible. So if we can have a function of 3 variables, like w equals f of x, y, z, for example, and let w take on certain constant values, we get level surfaces in r cubed instead of level curves in r squared, like in this example. So these describe the 3D trace of functions for various values of w. So it's like they have a trace in 3-dimensional space, but they live in 4-dimensional space. So what are the level surfaces of this function of 3 variables? Okay, that would be w equals f of x, y, z equals x squared over 4 plus y squared over 4 plus z squared over 4. What are the level surfaces? Well, if we put in w equals 0, we got x squared over 4 plus y squared over 4 plus z squared over 4 equals 0, so it's a point. But if we say let w equal f of x, y equal 1, then we got 1 equals x squared over 4 plus y squared over 4 plus z squared over 4, which would give us x squared plus y squared plus z squared equals 4 if you multiply both sides by 4. And that, you should see, would be a sphere of radius 2. So that level surface is a sphere of radius 2. If I let w equal, let's say, 3, I did 0 and 1, no, let's say 2, then we'd have the sphere x squared plus y squared plus z squared equals 8. And so that would be a sphere of radius 2 squared roots of 2. And if we let w equal 4, did 0, 1, 2, let's do 4, you could probably see that will give me a sphere of radius 4 would be the level surface. Again, we can't see the function because it's four-dimensional, but we can see its trace, its level surfaces in our three-dimensional coordinate system. And so MathCAD makes a lot of graphs, and I use that, but not all graphs of two variables can be made with MathCAD. Some examples are draw the following. Well, f of x y equals x squared plus y squared times e to the 1 minus x squared minus y squared. Actually, this one I can. And I just define the function, put it in there, and looks like a volcano or something similar to a volcano. Arising from the xy plane. Oops, I think my volcano just erupted. There. I don't know how that happened, but there's our volcano, and that's what this particular function of two variables looks like. Granted, you can probably see a few level surfaces drawn on the sides of it. Looks like the level surfaces would be circles for that one. Here's another one, f of xy equals negative 4x over x squared plus y squared plus 1. And what does that look like? Well, this is an interesting thing. I guess when x is a negative number, then this f of x is a positive, and so it goes up to maybe a peak at pretty close to 2, maybe when x is negative 1 and when y is 0. So here's the y value equal to 0, x is negative 1, so that reaches a peak at positive 4, x is negative 1, over, look here, negative 1 squared is 1, 1 plus 1 is 2, and so positive 4 over positive 2, and so we get a peak of 2, and if we wanted to get, see where does this bottom happen, by the way, you're already probably thinking, I bet we're going to talk about maximums and minimums of functions of multiple variables, and if you had that thought, and thought back to Calculus 1, you'd realize that you're right. We're going to do that very thing. By the way, the minimum for this one, I think, would occur when x was positive 1, and see if x was positive 2, then this would make this, the denominator gets bigger quicker because it's going to be squared. So positive 1, that makes x, or makes the numerator negative 4, and the denominator is still 2, so then we have a minimum value of z, f of xy, at negative 2, and I think you can see that the down here at the tip of that blue, z is negative 2. And you can see also that x equals 1, where that happens, right, where that bottom point is, and y equals 0. See, x equals 1, y equals 0, that's the bottom point. X equals negative 1, y equals 0 is the top point. And you can see that this graph has a maximum and a minimum. And yes, we will revisit much of Calculus 1.